All right, I think it's time. Welcome back to everybody. We are back on our normal homeworks and quizzes schedule. That means we have a homework for tomorrow and the quiz on Friday. And I just wanted to say publicly, I know Friday is the last day before the break, and we're having a quiz on Friday. I don't take joy in putting a quiz on the day before the break. But I do put a quiz on the day before the break, and I will expect you to be there. If you have some kind of extreme, travel disaster or something like that, and you are not going to be there, then tell me about it and let me know, and we can try and set something up for you to take the quiz beforehand. But and I don't, you don't have to tell me your whole life story, but I don't really like it when people are like, oh, I have to go home because the only time I can get a ride home is before the quiz. And I say, oh yeah, where are you from? And they're like, oh, I live in Milford or something like that. Like, come on, man. You can get a ride appropriately. Of course, it's up to you. It's not, because of the way our grading works, it's not a disaster if you miss the quiz. You will have a chance to do these questions again later. But anyway, all that to be said, I will leave it up to you to decide if your excuse is bogus or not. Please don't give me the bogus excuses. But if you have good reasons, or if you got a plane ticket, I respect the plane ticket more than I respect my roommates taking me to Trumbull before the quiz. All right, great. Let's continue talking. The homework for tomorrow has 3 topics on it, so there's going to be three things on the quiz: the L'Hopital's rule, integration by parts, and the trigonometric integrals. These are kind of, in my opinion, the L'Hopital rule and the parts are not so difficult. The trigonometric integrals can be kind of involved. That's what we did last time. And this topic is, I suppose, kind of a continuation of that, which is also quite involved. So what we're doing today will not be on the quiz on Friday, but it will be, eventually, trigonometric substitutions. So what we did last time was trigonometric integrals, and that was integrals of sine and cosine, powers of products of sine and cosine, like sine cubed times cosine squared. And if you recall, there was one trick you use when one of the powers is odd, the save one trick, and then another trick, a totally different trick that you use when both of the powers are even. And you just have to remember to do these tricks. Sorry, I meant to remind everybody also, our after the break on Friday of that week is our first big test, the catch-up test. Is that what I called it? Something like that. And so this will be your chance to you get another shot at all of the questions on the big list. There will be, I suppose, something like up to number 12 or 13. I'll say more specifically before the test, but you get to try them all. The ones that you already have full credit on, you can skip because you already have full credit on, but you can do all the other ones. Anybody got? We'll talk about it more, but questions about how that works? I hope that everybody's clear on how it works. And hopefully, as we've been going, you should be checking off the little things on your big list. That's the idea. You may want to look up your grades and put them on the list. During the test, you should bring the list with you so that you know which ones you need to try to do or whatever. If you have lost, I gave it to you on the first day, the printed out version of the list. If you've lost yours or if you're unclear about how many points you have on this or that, I'm happy to tell you what I have in my grade book. All right. Anyway, let's talk about trigonometric substitution. So, what we did last time, trigonometric integrals, was finding the integral of sine and cosine in various powers, right? This is about using the trig functions to do other integrals. By other, I mean integrals which, when you look at it, it doesn't seem to have anything to do with sine or cosine, but actually you can put sines and cosines into it and use some weird tricks to calculate the integral, all right? And the classic example of this is something that you probably saw this example. This is not, I don't know how much of an impression this example gave you, but you probably saw this example in your Calc 1 class towards the end when you start to talk about integrals. This is a hard integral to do. It's a little complicated looking. You might think to do the u substitution here using the inside of the square root. But that u substitution doesn't work because the inside of the square root would be 1 minus x squared, and then the du would be negative 2x dx, but there is no negative 2x. That extra x is not present. And so this is a hard integral to do. But this you can realize as an area, an area, that curve, square root 1 minus x squared, is actually the curve that defines the top half of the unit circle. And this is a weird thing that is not obvious, but that, this is y equals square root 1 minus x squared. Another, if you simplify this by taking square on both sides, it cancels the square root, and then you can rearrange it. It's this, x squared plus y squared equals 1, which I hope you recognize is the equation of a circle, all right? So that integral that we're talking about is actually the area under the curve of a circle, and because we know the area of a circle is pi r squared, the r here is 1. The whole circle has area pi. What I'm looking at here is just 1/4 of the circle, and so this answer actually, the area equals pi over 4, all right? This is an example of an integral where you can't use any of the standard tricks to do the integral, but if you somehow realize that this is some recognizable area, you can figure out the integral is pi over 4, all right? What I don't like about this is it requires that you sort of think of this as an area and then draw the picture and figure out what the area is. So the big question, and this is what trig substitution is used for, can we do this integral, 1 minus x squared dx, using, I'll just say, weird tricks, parentheses, not as an area, right? Because I usually, when I do integrals, I don't want to be thinking about areas of this or that shape, all right? Or for example, if I asked you, instead of the integral 0 to 1, what about if I want to do integral 0 to a half? That would be only this far. What would this area of just the red part be? My answer is, even though I understood this is a quarter circle, what's that? I don't know. It's not 1/8 of a circle, it's a little bit bigger. That's just something, I have no idea what that area is. And so my method here is not good enough to answer even very similar questions. Cannot be answered by this area method. So can we do this using some other weird tricks? And the answer is yes. And what is the weird trick? It's called this trigonometric substitution. Let's try this example. This is kind of an easy one, and then we're going to do some other ones as we go. Here is the trick. So I'm going to do 0 to 1 integral 1 minus x squared dx. All right. This is going to look like kind of out of nowhere, but we're going to talk about how you would recognize what to do here. I'm going to do the substitution. Sorry, I got dots. Do the substitution. X equals sine theta. This is something I was mentioning last time. This is a slightly weird type of u substitution, which our book calls the inverse substitution. Usually when we do u substitution, I tell you what u is in terms of x. But here, I'm just telling you what I'm going to replace x by. I'm going to replace x with sine of theta. All right, and that means dx, as usual, dx is the derivative of x. And so that would be cosine theta d theta. And I'm going to change this integral, which is currently written in terms of x. I'm going to write it instead in terms of theta and d theta. All right. In order to do that, we also have to transform the boundary values of 0 and 1. So I have to say, when x is 0, that means, in terms of theta, this would say 0 is sine theta, right? I'm just taking this here and plugging x equals 0. It says 0 equals sine theta, and then I can solve that for theta. Can anybody say what is the angle which gives you 0 when you take the sine of something equals 0? I think I heard somebody say it's also 0. Sine of 0 is 0. So theta in this case is 0. And what about the top value? I'm trying to transform these two numbers, right? They are, as written, they are numbers, values of x. Since I intend to rewrite everything in terms of thetas, I have to translate these into values of theta. So x equals 1, that is to say 1 equals sine of theta. And what is the theta which gives you 1 when you take the sine? Yeah, this would be pi over 2, 90 degrees. Sine of pi over 2 is 1. So this is theta equals pi over 2. And so when I change the integral by plugging in all of this other theta stuff, I'm going to change the number. 0 to 1 instead will be 0 to pi over 2. Because x equals 0 is still 0, but x equals 1 is pi over 2. All right, let's plug it all in. So this is, we are substituting, instead of x's, I want to write everything using thetas. 1 minus sine, x is sine theta, which means it says x squared there. I get sine squared theta. And then outside, dx is cos theta d theta. All right. We are changing all the x's and dx's into thetas and d thetas. Now, to me, this is actually more complicated than what we started with. Usually the idea in doing a substitution is that the thing that you're working with becomes less complicated. It simplifies, although this, I mean, we have now like an extra thing over here and more stuff inside. But we can use our various things about the trig function, sines and cosines. There is actually a way to simplify here. I'm looking at 1 minus sine squared. Anybody see what we can do something with that? One minus sine squared. This is part of the bunch of formulas we used last time, I think. That's not wrong, but not very helpful. He said, can we factor it as 1 plus sine theta times 1 minus sine theta? That's actually true, but I don't want to do that. Not everything permissible is beneficial. What do they say? That ain't wrong. Got an idea? Yeah, 1 minus sine squared is the same as cosine squared. This is a trick that we were using last time. Maybe I'll just write it down so we're all clear. 1 minus sine squared theta is cosine squared. And depending on what's going on, you sometimes want to do it the other way around. 1 minus cosine squared is sine squared theta. All right. So inside the square root there, it's cosine squared. And I like the looks of this because the square root of cosine squared is just cosine, all right? The square root of a squared is whatever the original thing was. So now I have 0 to pi over 2. This is just cosine theta, and then another cosine theta, d theta. And so what I end up with is cosine squared theta. All right. The whole point of this trick is right here when the square root goes away. All right. Principally, when I look at this, like the problem as originally stated, what I don't like about this is the square root. That's the only reason this is a hard integral to do, is because of the square root. And this entire weird trick here is to facilitate that step right there, where the square root cancels with the square. You have to realize that the inside of this is actually the square of something, and then you can do the square root. All right. Anyway, we're not done, but we have reduced the original thing into this, and this, my friends, is a trigonometric integral. This is what we talked about last time. It is a power of a cosine. All right. And this is, what we talked about last time was if you have a power of sines and cosines, you choose either one of those two tricks. If there's an odd power, you do the save one trick. And if there's an even power, you do that other trick. And in this case, we have to do that other trick. There's no odd powers here. All the powers are even. But anyway, I'm going to say this is a trigonometric integral of the type that we did last time. I don't know if you remember how to do those tricks from last time, but in this case, cosine squared of theta, the appropriate thing, this is the old half angle formula. It says cosine squared theta is 1/2 1 plus cosine 2 theta. Remember that one? We were talking about these last time. You should be able to flip back in your notes and make sure that I got it right. Like I said, these things are ones that I often mess up myself, but that's what it is, all right? So I'm going to plug that in to the integral, and we can continue. 0 to the power over 2. So instead of cosine squared theta, I'm going to write 1/2 1 plus cosine 2 theta. Like that. And now this is a pretty straightforward integral. We can pull the 1/2 out of the integral sign, and then we just have, two things, and we integrate them one by one. So this is 1/2 on the outside, 0 to the power over 2, and then I have 1 plus cosine 2 theta. And then we do the integral. 1 being just a constant becomes theta, right? The integral of a constant is just that same constant times, well, it's usually times x, but the variable is called theta here. So it's times theta. So it's like theta, and then plus cosine 2 theta. The integral of cosine is sine, and the effect of that 2 on the inside gives me an extra 1/2 like that. So this is 1/2 sine 2 theta. And I plug in 0 and pi over 2. All right. Almost done here. Plug them in, and then, see if we can simplify as much as we can. 1/2, and then I got pi over 2 plus 1/2 sine of 2 times pi over 2 minus, and then plug in 0 everywhere. 0 plus 1/2 sine of 2 times 0. All right. Often you won't be able to simplify anymore, but actually these are easy enough that we can simplify. I get 1/2 here. Pi over 2 is just what it is. 1/2, this will say sine of pi, and then subtract 1/2 times 0 is 0, and then 1/2 sine of 0. And what are all those things? Sine of 0 is 0. Anybody remember sine of pi? That is also 0. Yes, I'm glad to see all of you remember your sines and cosines. At least one of you does. So yeah, both of those signs equal 0. So actually everything here is 0 except for that pi over 2 at the very beginning. The whole thing is just 1/2 times pi over 2. Pi over 4. Can you believe it? That's the answer I said at the very beginning, that 1/4 circle area was pi over 4. If you didn't like the area business, this is how you do it sort of for real, by hand. All of this. It's quite a journey to get there, but this is how we do it, and the answer is correct. Pi over 4 is what the answer ought to be. All right. Anybody got thoughts about this? I got one more to try, and then I have one for you all to try. Let me just say, in general, so the big question on your mind at this point should be, you really expect me to do all that? Yes. The real big question is this: how did you know that this is the substitution you were supposed to do? And this substitution works whenever you see something that looks like that inside of a square root. I would just say very specifically, when does this substitution work? So I'll say generally, if you see this is slightly more general. In our example, it was just 1 minus x squared, but actually you can do this even if there's some other weird number in front of the x squared. So generally, if you see a squared minus x squared inside of a square root, you should do the substitution x equals a sine theta, in which case dx is a cosine theta d theta, all right? This you should put in a box somewhere and remember this. So when you look at the integral, if you see part of it that looks like that, square root a squared minus x squared, this is the appropriate trigonometric substitution to do. And the key step, you do this substitution, and you use this as the key step, sorry, a squared minus a squared sine theta, sine squared theta equals. That's the key step inside of the, as you're doing the steps. You know, in our case, the a was just 1, but there was one step in which we had 1 minus sine squared theta, and we turned it into cosine squared theta. And that's really the whole point of doing this substitution, so that you can do that step. All right? This is the general procedure for trig substitution of this type. There's actually other types that we're going to talk about, but this is sort of the standard one. If you see that, this is what you should do. All right? I got another one, and then I have one for you all to try. Let's see if we can. So I'm going to put this in a box or something. You got to remember this. All right, let's try integral 0 to 3/2 x square root 9 minus x squared dx. All right? Now this one has an extra x in the front, which I'm going to, hopefully that will just kind of work itself out. I'm going to ignore that for now. When I see square root 9 minus x, that reminds me of this. And so I'm going to do this kind of substitution. What am I using for the a in this example? What I want to see here is a squared. So it's 3, right? This is a 9 here, which I think of as 3 squared, which means my a is going to be 3 here. So here, a is 3. That's so that a squared is a 9, right? And so what I'm going to do for my substitution, I substitute x equals 3 sine theta, right? A is 3. And then the dx, being the derivative of that, is 3 cosine theta d theta. So this is my substitution that'll sort of get us going, at least. All right. We also, as always, I didn't mention it in the box there, but we also have to change the boundary values, 0 to 3/2. You got a question?
For a, will the thing in the square root always be a perfect square?
No, if I'm being charitable, it will be. But if this was, say, 7 instead of 9, you would use square root of 7 as the a, which, I mean, is kind of a pain, but it's not really any harder. It's just you may, if that's not a perfect square, then this, instead of a 3, you'll have some weird other constant. But it'll still be a constant, so it's not a big deal. Yeah. I'm pretty much always going to make it a square just as a personal favor. It's the kind of guy I am. All right, great. Let's continue. So I'm going to change the boundary values. You have to figure out, and this requires that you can do your values of the trig functions fairly well. So when x equals 0, that's the lower value. That means 0 equals 3 sine theta, and I have to solve for theta. The way we do this is we just take my substitution and plug in the various values of x. There's x equals 0, or there's x equals 3/2. All right. Solve this for theta. We can divide 3 on both sides. It'll still be 0 then. 0 equals sine theta. Theta equals 0. All right. That's because sine of 0 equals 0. So my lower boundary value is a 0 still. My upper boundary value for 3/2. This one is going to be a little more interesting. I will say 3/2 equals 3 sine theta. And again, try to solve for theta. I would get sine theta all by itself by divide on both sides by 3. The left side will then say 1/2. This is 1/2 sine equals sine theta. Anybody else recall what's the angle where the sine of something equals 1/2? Yeah. Pi over 6, he says. Yeah, I agree. This is 30 degrees, otherwise known as pi over 6. These I will, I've been saying all along, I will continue to say, you got to know how to do this. This is not going to go away, and you'll be kind of screwed in these kinds of problems if you are not able to do that little step there. So you may want to review yourself. I'd be happy to help out, but let me know. All right. so these are my two boundary values now. The integral, when I transform it, will go 0 to power over 6. All right, let's do it. So we can plug everything in. Integral is now 0 to power over 6. And then we're going to replace every x with whatever in terms of theta. So the x on the front becomes 3 sine theta. Then the square root, 9 minus x squared. 3 sine theta squared. And then outside dx, don't forget dx does not just turn into d theta. Dx has its own little formula. Dx is 3 cosine theta d theta. 3 cosine theta d theta. All right? And as usually happens, it looks like it got more complicated at this step, but we can do a fair amount of simplifying. Make sure that you have these parentheses right here, because when I square this 3 will get squared and turn into a 9, which is actually good. That's what you want. You want the 9 to like match up with this 9. So we're going to square 3 sine theta, the whole thing squared. Can I say, first of all, this big integral here, I have this 3 and this 3, which can both come out of the integral. So that's going to be a 9 on the outside. I have sine theta at the front, and then square root. And now I'm gonna square out 3 sine theta, the whole thing squared. You just square each of those things. That's 9 sine squared theta. And then on the end, cosine theta d theta. All right. And what do we do with 9 minus 9 sine squared theta? This I wrote in the box. I said do this simplification and use this, right? This is the step at which we are at right now. 9 minus 9 sine squared theta is 9 cosine squared theta, right? A squared is 9 in our example. So inside the integral, inside the square root sign, it now says, come on now, sine theta here. Okay, inside there, 9 cosine squared theta. Right. And now we can do the square root. Inside the square root is just 2 things multiplied together, which means you just do the square root of each of them. The 9 gets a square root, it becomes a 3. The cosine squared gets a square root, it becomes a cosine. So this is going to be 9 integral sine theta, 3 cosine theta, and then cosine theta d theta. All right. That was the key step at which we dealt with the square root. The entire, like I said before, the entire purpose of this trig substitution really is to deal with the square root somehow. And that's where it happened. All right. We're not done by any means, but we can simplify here. That 3 can also come out of the integral. So we get 27 in the front, 0 to power over 6. And then I have 2 cosines and a sine. So I'll write it as cosine squared theta, sine theta, d theta, right? 2 cosines and a sine. And how do we finish this? Now, this is a trigonometric integral. It's a product of powers of sines and cosines. So we do the stuff that we did last time. Remember, there were two variations. One, if all the powers are even, you do it this way. And if there's an odd power, you do it this way. Actually, that's the case in this example, because I have sine. This is like cosine to the 2, sine to the 1, and 1 is odd. So I can do the save 1 trick. And this is like conveniently already saved out here for me. So this, I do save 1 sine. And it's already split out, sine theta, d theta. I hope you remember this is from last time. I don't know if you've been doing this every night over the weekend, but you save the sine and you make the cosine into the u. So you do a substitution, u equals cosine theta, and then du is minus sine theta d theta. And so this integral now says 27 integral u squared times negative du. And now it's finally simple enough to actually do the integral. This is the save 1 trick. All right, we're getting there. Almost done, maybe. Do the integral here. Integral of u squared is going to be 1/3 u cubed. I suppose 27 times the third makes it go back to 9. You're dividing out one of the 3's. Negative 9 u cubed. And we do have values to plug in, but those values to plug in, 0 and pi over 6, those are values of theta. So we have to unwind the substitution, just like we always do with the u substitution. You plug, usually I say plug the x's back in. It's not called x, it's called theta in this case. This is minus 9, and then u cubed is actually cosine theta cubed. And then I'm going to evaluate. Finally, 0 and pi over 6. And this will be it. So we get minus 9 cosine pi over 6 cubed minus 9 cosine 0 cubed. And these values, I hope you know. Cosine pi over 6. Pi over 6 is 30 degrees, so I would think of this triangle. And you just have to remember the sides of this triangle look like that. The cosine there would be adjacent over hypotenuse, which is √3/2. This is how I remember my values. You may have remembered them in a different way, but whatever. √3/2. It's that cubed, and then minus cosine of 0 is 1. So that inner cosine of 0 is just 1. This is just going to say plus 9 then. And that's the answer. All right. It's quite a journey to get there, in my opinion. Anybody got any questions? I would say, as far as our big checklist of topics, this is probably, I don't know if I would say the hardest, but I would say if I give you one problem, it's going to take you a long time to work it out all the way to the end. All right. This is probably the longest single problem that you'll see on one of our quizzes or tests. The trig substitution. I can't even scroll it all at once. It's that. If you could still see that. All right. I got one for you all to try. Chat with your friends about it if you like. See what you think about this one. The integral 0 to 2 over √2 x squared over square root 4 minus x squared. See what you think. I'll give you the back of the book just in case you actually make it to the end. The answer should be pi over 2 minus 1. See if you can actually get there. It's not worth trying to reverse engineer this answer. There are many, many steps in order to get there, but once you get to the end, this will be how you can see if you got it right. Feel free to chat with your fellows. You might do something later on, you might want to rearrange things, but too close.
That's good, yeah.
You changed the boundary values?
That's why
theory toward 2
How do I do this?
square root of 2 divided by 2 is just
What do you do to find the boundaries?
we do x equals the current boundaries, so you already have x equals something, and in this case it's 2 sin theta. So you just plug for x, lower boundary being 0, you're doing 0 equals 2 sin theta, and you divide by the constant. Yeah, and you divide by the constant sin, and here it's still 0, and you end up with 0 equals sin theta, and then
I was
theta
looking at
sin.
it. Okay, I couldn't do it.
That's what happened.
No, I'm just gonna say it would be stupid. Yeah.
Oh.
Hang on, I was.
It's 2 rad 2 equals 2 sin theta.
Sorry.
2 over rad 2 equals 2 sin theta.
Exactly. You need to like 2 over the square root of 2 by 2, but
I didn't do that.
I think it's 2.
Yeah, I think no, that is right.
Here, I would say the Bible
It's just square root of 2 is 20. Don't ask.
It stays the
What
same.
it is. No, just focus.
Oh, rad 2 on the top?
that is amazing.
And I forgot another.
Rad 2 over 2?
Yeah.
Yeah. And it's, yeah, it's just identifies it too.
That's not.
It may do better. One
So
over
now we do know that 2 C theta is right.
that's on the hand. It goes.
Say root 2 over 2.
One here.
I feel like at some point we gotta get rid of that fraction. I don't like that.
It's like we have everything else we need.
Do we read the square root?
I've been wondering to myself, why is that?
That's just sub and C, I guess. So, oh, and then change the boundaries. So from 0 to pi over 4. We get to switch all the x's. So we get 2 sine theta, the whole squared on top. And then square root of 4 minus the whole squared is 2 sine theta.
Then we have.
How's it coming here?
Right there.
That's good.
I don't. Should we get rid of the fraction or no?
No, you can keep the fraction.
No.
Yeah. I would say do something in there, try and simplify that stuff.
And then add another 2 cos theta instead of dx.
I've had the same conversation with several people. 1 over root 2 and root 2 over 2 are the same thing. These are the same number. If you do this like rationalize the denominator trick that you learned about in high school, you get that from that. So if you don't recognize this, but you do recognize this, they're the same thing. It's powerful.
I have this. It looks sloppy, so this is 4 minus sine
No,
theta
you're
squared.
missing a 2. X is 2 sine theta. And the whole thing squared is x squared.
You still basically kind of just do 2 sine theta times all of this.
Yeah, like the X up top.
Okay.
Yeah.
Hey, welcome. And then don't forget the 2 cos theta dx.
You guys doing all right still?
Oh, yeah.
Dx here.
It's with, are you supposed to pull, like, what do you do here?
So it's 2 sin theta d squared. So you apply the square root, and you apply the square to everything. So you end up with root of 4 minus 4 sin squared. And then you apply this little thing here, like where you have a squared minus a squared sin squared, and gets you a squared cos squared. It's actually where I am right now.
So 4.
Yeah, no, this is I would say.
I also have been putting the 2 cos theta dA without touching it. What's supposed to do with it? Oh, wait. Look at this. If here, this is going to become just 2 cos theta. Can that just cancel out? Yeah, it does actually. Look. You have this, and then you do square root. You have 2 cos. Just 2 cos theta. And the whole thing times cos theta, and then you can just cross them out.
Who's this?
So from here, this turns into 4 cosine theta.
4 sine.
I mean,
Oh, that turns into 2 cosine squared. What am I saying? No, it turns into 4 cosine squared.
4 cosine squared.
Yeah.
Yeah, because I had this
This has been saying what's the answer? I would do this one. You can just sine squared theta. There's no short, this is right. And then sine squared theta is actually 1/2. So it's going to be 4. So 1 minus cosine squared. No, wait. Cosine 2x. Okay. Cosine 2.
Well, I guess it's a constant. So we can take it out.
This is like cosine squared. Yeah.
They're not even.
The one that I just did.
This is cosine cubed. So the same one.
We can also pull out the 1/2 now. So 4 times 1/2 is just 2.
No, because it's fine if there's one.
So yeah.
As long as you have one.
Can I say something about this? Yeah. One with sine is sine squared.
So I'm here so far.
When I get to heuristic,
I can do the same one.
What do you have?
pull out the two.
Wait, what?
2 sine theta squared times
How do you still have two?
that.
This should be 4. Because it's the whole thing squared here.
Okay.
Yeah.
Oh wait, actually, I'm sorry.
Should be it, and then just plug. That's pretty much it.
So this
What
should
is
be
it?
4, then you can pull it out.
Exactly. And then you do like the trig for the sin squared, which becomes 1/2 1 minus cos 2 x basically. And you just pull out the 1/2 thing.
How you guys doing?
This actually is, we had to better because cosine on the bottom and goes off.
Tell me I'm wrong and come again.
You literally take like the whole page.
It really does. I think we're pretty close to realizing like this is looking.
Yeah, I think this is. Does it equal that?
I'm not there yet, but
No, I think this is good. Yeah. Are you getting there too?
You know, I'm getting there.
Yeah, sine squared of theta, and now you use that weird 1/2 angle formula, which I used it a few minutes ago. I used the
Don't ask me nothing. Just be calling me.
that one in green,
Oh, okay.
but do it with sine instead, so that the corresponding one for sine is the same but with a minus.
So it's 1 minus sine.
No, it's still a cosine.
Still cosine.
How'd it go? You worked it out?
Where are you getting your phone? They're gonna wait.
I must have no effect because I took out the 2 before I came. I took out the 2 before I came.
So I get 4.
Maybe it's
Oh, that's like taking the integral of sine squared theta is this.
works out.
well, that's not the integral actually. It's just
So
it's just like one of the tricks that we did like sine squared of x is 1/2. Like you just plug it in instead and then you can see like you still is part of the integral. Yeah. And then you
So
can
did you pull out the you pulled out
you pull out the 1/2. That's 0. Right, so it's just that. And I really don't want to like simplify this. Pi over 2 minus 1 some shit. So if I
Yeah, you did this. You guys at the part that's like 4 integrals
So now when I get to 1 minus cosine 2 beta, I can
All right, can we go over these? I saw several people made it to the end. Like I said before, this is very long-winded. procedure, and it's really easy to make mistakes along the way. Although I saw, people doing fairly good progress.
I think that's the answer.
So anyway, the proper substitution to do is x equals 2 sine theta, which means the dx is 2 cosine theta d theta. And I need to change the boundary values. I think everybody eventually settled on x equals 0 gives theta equals 0 and x equals 2 over root 2. This means that theta is pi over 4. When you set it up, you end up saying sine theta equals 1 over root 2, which, if you like, is the same as saying sine theta is root 2 over 2, which is pi over 4. Somebody showed me a cute trick with the fingers in the hand. I've never seen this before. He left the room. He taught me something today, which I don't fully understand. But you do the thing with the fingers. That's how you do this this pi over 4. I'll do some research on the finger method. Anyway, when I plug everything in, it becomes integral 0 to pi over 4, and then x squared up top becomes 2 sine theta squared, which if you square it out is 4 sine squared theta on the top. And then on the bottom, square root 4 minus 4 sine squared theta. And then dx is 2 cosine theta d theta. All right, I'm skipping a few steps just because I know everybody mostly did all this stuff. And then the final sort of weird, cute little trick is on the bottom here, you replace this with 4 cosine squared theta. And then I will be ready to just sort of do simplifying and canceling. So on the bottom, this is square root 4 cosine squared theta, 2 cosine theta d theta. All right, and then we can actually do the square root on the bottom. Can I say something that sort of makes me makes baby Jesus cry? Sometimes people do this much, and then inside the square root here, they go, this is 2 minus 2 sine theta. It makes me hang my head and shake it back and forth slowly. Don't do that, because you can't do that under a square root when you have things added together. You can't just do the square root of each of them. In fact, if you could do that, you should have just done it at the very beginning, and then we wouldn't have talked about any of this. The whole reason we are talking about this at all is because it's hard to handle this square root. You cannot just take the square root. But here you can, because there's no more addition inside the square root. Everything is multiplied, and you can just do the square root this time. So anyway, this like so. 4 sine squared theta. On the bottom, I do that square root. It becomes, the 4 becomes a 2. The cosine squared becomes a cosine. And then times 2 cosine theta d theta. All right? And then the magic happens. To me, this is like a very long-winded and kind of laborious process. But I don't know about you. I do feel some kind of satisfaction when you can do that. And I feel like, oh yeah, it feels so good to cancel like that. What remains then is sine squared theta d theta. I pulled a 4 out. All right. I hope that you got this far. Any questions about that? Like I said, there are a lot of opportunities to mess it up, but this is what it should be. And now it is a trigonometric integral of the even exponent type, and so I should use that weird half angle formula inside the integral. Makes it 1/2 1 minus cosine 2 theta d theta. Pull that 1/2 out. 4 over half, or 4 times a half, 4 over 2 is 2 on the outside. 0 to pi over 4, 1 minus cosine 2 theta. Do the integral. We're almost done here. Theta minus 1/2 sine 2 theta. How am I doing? I don't know why this paste keeps coming up. I don't want to paste. All right? And then you plug the values in, and hopefully everything equals what I said it ought to equal. Pi over 4 minus 1/2 sine of 2 theta. Theta is pi over 4, so 2 times that would be pi over 2. So this is sine of pi over 2. And then subtract 2, 0 minus 1/2 sine of 0. All that stuff is all 0. And then the stuff on the beginning sine of pi over 2 is 1. And so this says 2 pi over 4 minus 1/2. That's because sine of pi over 2 is 1. And if you distribute the 2, you do indeed get what I said, pi over 2 minus 1. All right? When this appears on the quiz, there will not be a A's and B's part. This is long enough. Any questions about that? You really do need to practice these so that, like you've discovered, there are lots of chances to mess it up in there. All right, excellent. So that is the trigonometric substitution. I got a couple variations or other, related things to say, but this is the basic procedure, and the variations are not really harder than this, but just like some other things that may come up. So we can do it, I will say, what about indefinite integral? That's indefinite means you don't have the little numbers to plug in. All right. Usually that's easier because it just means instead of plugging the numbers, you put the plus c, and that's all there is to it. But actually, in these ones, the indefinite integral makes you do a little something extra. For example, let's try this one here. Now, this one is actually exactly the same as the one that I did a few moments ago. But I want to talk about what if you hadn't had values and you just want to do this as an indefinite. This is the same one. So as an indefinite, I will just say we do the same trig substitution. In this example, it was x equals 3 sine theta. Dx equals 3 cosine theta d theta. All right. And I don't think we need to go through all the steps. It will take a while. But if you do all the same steps, equals, etc., etc., etc. Let me jump down. So I'm going to look back at my notes here. Eventually, when we did this one, we got all the way down to, eventually, you did a whole lot of stuff and ended up with this. And then we plugged in 2 values, all right? Now, I'm not going to do the values this time, but when we did this before, this problem ended at this step. So we did the whole procedure and then plugged in the 2 values. Now, I'm not going to plug in the 2 values because we don't have the 2 values here. Instead, I put the plus c. So forget about the values. I say plus c. The problem is we always should write the answer using the original variable, which is x. And right here is not clear. How do I write this in terms of x? So we must write it in terms of x. And what is x? Well, x is sine theta, right? I mean, with the 3. Whatever, we could probably deal with the 3. But x is sine theta, and there isn't any sine theta in here at all. So what is this even? Like, is it even possible to write this in terms of x? This is the dilemma. You might say, well, cosine theta is dx, so maybe the answer is in terms of dx, but that actually doesn't make sense. When you're doing an integral of something, you shouldn't have dx in the answer of an integral. That means you messed it up somehow. So we have sort of a real problem here. And the way to do this is you look in here. You solve for theta here in terms of x. And then you can plug that in for theta, where you see theta above. Solve for, I wrote those like one word. Space it out a little. Yeah, solve for theta in terms of x. How would I solve for theta in terms of x here? X equals 3 sine theta. All right, I guess I would divide by 3 first of all. X over 3 equals sine theta. Anyone know how can I solve for theta here? Don't say divide both sides by sine. Sine is not a thing you divide by. What do you say? Do the inverse sine on both sides. Yeah, you have to use the inverse trig function here. If x equals 3 is sine theta, that means theta equals I went green. Theta equals inverse sine x over 3. This is how you solve for theta. You have to, so these problems, if you're not given the boundary values, you're going to end up doing the plus c, and usually your answer will involve inverse trig functions. Because if, I mean, this basically always happens. If that's the substitution you make, and you have to solve it for theta, you must use the inverse sign in order to do that. So it's like this. So then, my answer becomes -9 cosine of inverse sine x over 3, whole thing cubed, plus c. And that is a legitimate answer in terms of x, the original variable that we were given. All right. I want to say one more thing about this. So this is the correct answer, but I may, just because I'm that guy, I may say simplify this so that there are no inverse trig functions in your answer. And this is something that we talked about a couple weeks ago. I think actually we talked about this on the video when I was on one of my trips. You want to hear a crazy story about one of my trips? So the trip that I was complaining about before was when we went to Seattle, and I messed up our hotel reservation and the flights were all delayed. So the trip was my kid is applying to colleges, and he's applying to music schools, and so he has to do an audition, and that's why we had to go there to do the audition in person. And you have to apply to the school, and then you also have to do the audition, and you have to like get admitted as a student to the school, but then you also have to pass the audition for the music school. And we haven't heard back. You hear back from them like separately. So we didn't know if he was accepted to the university, but he did the audition anyway. And during the audition, they said, like when the audition was over, they were like, "You did a great job, and as long as you get into the university, you'll get into the music program." So we're like, "Oh, that's great." And then last week we got a letter that said, "We're sorry, you did not get into the music program." We still haven't heard from the university. It's crazy. I don't know if he would appreciate me telling you all this. I think it's a funny story. I'm not trying to shame him for not getting into the audition. It's crazy. They told us he would get in, and then he didn't. It's great. Any thoughts about that? I think it's crazy. Yeah. He didn't really want to go there anyway. We didn't really like the place. The whole music stuff was like in this like wet, dirty basement. It wasn't great. It wasn't a great facility they had. Anyway, as I was saying, you can simplify something like this, and this is something that was discussed. I don't think we ever did this kind of like in person, but this right here we can simplify. We can write this actually not using any trig functions or inverse trig functions. And when I ask you to do one of these, I might say, simplify all of the trig functions in your answer, or write the answer so that you're not using any inverse trig functions. All right, how do we do this? The idea, if I will refresh our memory here, when I see inverse sine of x over 3, this is an angle where the sine, of course, sine is opposite over hypotenuse. I hope everyone remembers that. Where this is an angle where the sine is x over 3. That means I want to think of this as the op over the hype. X is the op, and the hypotenuse is 3. All right. So I'm going to draw a triangle which has these things. That's the angle I'm talking about. The op is x, the hype is 3, like that. This is the triangle I'm talking about. Inverse sine of x over 3 actually is that angle. So this angle right here is inverse sine x over 3. This is weird, but that's what all of this means, all right? And what I kind of underlined in green there that I said I want to simplify is the cosine of that angle. But you can do the cosine of that just using the triangle, right? The cosine is adjacent over the hypotenuse. The adjacent is the one on the bottom, which we unfortunately don't know. but you can find that by using the Pythagorean theorem. This is a right triangle, all right? So I can find this side here. This is the Pythagorean theorem. It says, if I call that a squared plus x squared equals 3 squared, right? And this, you can solve for a. It is, 3 squared is 9. I subtract the x. So this says a squared equals 9 minus x squared, and then take the square root. A is like so, all right? That's the adjacent side. All right, and so what is the cosine of that? So that means in this triangle, cosine of this inverse sine x over 3, is adjacent over hypotenuse. Adjacent is that a that I wrote there. Root 9 minus x squared over hypotenuse is 3. And here we have written it without using any trig functions or inverse trig functions. All right. So what's my final answer then? The whole point of that was to simplify that sort of green bracket up there. All right. But anyway, my answer will be, so this integral, this is really the end here, minus 9. And then instead of that stuff, cosine whatever of inverse sine, it's just this root 9 minus x squared over 3. And it was inside of a cube. That big cube there was just from before. There was a cubed in the thing that I was trying to simplify. That's my final answer. All right. So we have this like extra little step at the end there. Maybe just because, we have another type of thing. We don't have nearly enough time to do another example. Could I just try to get you to try one of these? So you need to know how to simplify one of these weird things at the end of one of these problems. So how about, just in our remaining few minutes, can you try? Your job in each case is to simplify these. You can do it with tans also. Really doesn't matter what these things are. See if you can simplify both of those. And then I think that'll do it for today. Each one you should draw a triangle using the appropriate op and height or whatever. The first one, you should start by drawing a triangle where the sine is 5 over 2x. Put those as the opposite end of the hypotenuse.
it's 2x the whole thing squared, which is 4x squared. This should be 2x the whole thing squared, which is actually 4 times x squared.
4 times x squared.
Because it's 2x squared.
Mm-hmm. Oh,
So
okay.
it should be right with parentheses in there.
Got
You
it.
square the 2, you also square the 2.
Okay, okay.
Yeah, that's good. This, so the answer is just that. It's, you're taking the cosine of the situation. It's not rapid. The whole point of doing this is to do the cosine of the other side. Well, it's more like that, just equals that. We're not doing anything else. Although ordinarily this is the last step in the solution. All good here? Sorry I didn't get it all around. Let's go over these just because we got to go in a moment. So the top one, I start by drawing a triangle where the opposite sine is opposite over hypotenuse. So I put the 5 there and the 2x there. All right, and this I'll call a, like I usually do. And then a squared plus 5 squared is 2x squared. Make sure you have these parentheses. When I do 2x squared, that ends up looking like 4x squared. So this is a squared plus 25 equals 4x squared. And then solving for a, you subtract the 25 and then take a square root to get the a by itself. It's 4x squared minus 25. All right, that's the a in this case. This square root, you cannot simplify. You got to just leave it like that. You can't do the square root of each of those two things because they're being added together. There is no such rule for the square root. And anyway, now I just do the cosine of that. The cosine of this. And that would be the adjacent over the hypotenuse. So it's that over 2x. So my final answer would be cosine of inverse sine. I'm just writing what we started with again. Is the a, that's the adjacent over the hypotenuse. Like that. And this can't be simplified, at least not in any ordinary way. I would leave it like that. Questions about that one? All right, and then the other one is similar, but tan of inverse cosine x over 5. So this time I begin by drawing a triangle where the cosine is x over 5. That's the adjacent over the hypotenuse. So I begin with this triangle. The cosine of this is supposed to be x over 5. And then I can find the other side, again, by doing the Pythagorean theorem. If I call this, maybe I'll call it b this time. You can call it whatever you want. X squared plus b squared is 5 squared, which is 25. So the b, if I solve this, subtract x squared, take a square root. 100 minus x squared, like so. That's the b, and then my final answer will be the tangent of this, which is opposite over adjacent, which is b over x. So this thing equals b over x. That's the tangent, and b is what I said it was. So root 25 minus x squared over x. There you go. I hope you got that. All right. See you next time. See you tomorrow. Let me know if you want to chat about the homework. I'd be happy to.